So looking at page 8, we're going to get at the generalization of these processes for finding a Riemann sum rectangular approximation. So find an expression that can be used to find the upper and lower sums for the region bounded by the graph of f of x and the x-axis between a and b for general n. All right. So what I'll do is draw a general. Well, we're going to keep things as general as possible. So I'm going to draw a general function. I'm going to draw it over some arbitrary interval that I'm calling a to b. All right. So as we go from left to right, we can have any number of different rectangles, but their vertices have to be on the upper left-hand corner. All right. So if I draw, and we'll just kind of use our imagination here. I'm going to draw n rectangles. Here's one, or an attempt at one. A little wonky, but hopefully you see what I'm going for here. Very wonky, too wonky possibly. Alright, so just kind of populating the entire interval. So it's going to be kind of 1, 2, skip a few, and then finish the job. Because we're not going to be able to get too specific in terms of the actual coordinate values here. So there's no point in drawing every single one of them, but you get the idea. We're propagating. We're filling in using the trend from left to right. All right. So what we learned on the previous pages is that b minus a divided by n would give us our delta x. That's great. All right. The issue is in previous pages we had a b, we had an a, and we had an n. Here we still have a b, a, and n, but they're specifically b, a, and n. All right, so our delta x, that little tiny distance between verticals, that's delta x, that's going to be known as b minus a over x instead of like a quarter or a half or something. All right. So we have to start thinking about, okay, well, what does that mean in terms of the important values for the rectangle? All right, so the first important value here would be the a value. I'll use the highlighter like I did previously. So your a values, followed by a increased by delta x. So now, just kind of going further in the process, what did we do? We took each of those x values and popped it into the original function. So the point on the curve that's going to be relevant, this point here specifically, would be a comma f of a. The second point is the a value increased by delta x, so a plus delta x. Now whenever you evaluate a function, you plug the x value, quote unquote x value, into the function. So f of a plus delta x. The third point, well, we're going to have two of those delta x's. So it's going to be, I'm going to bring it in a little bit more, a plus 2 delta x, comma f of a plus 2 delta x. And then I'll just do one more, a plus 3 delta x, and f of a plus 3 delta x, and so on. All right, so we could start kind of generalizing here a little bit. I mean, everything's in general form, but we could start kind of going through the process. All right, so the values on the x-axis that are used to find the rectangle areas, well, we have the a, we have the a plus delta x, a plus 2 delta x, a plus 3 delta x, and so on. All right. Now, just to get to the part where we generalize this a little bit quicker, or a little bit more efficiently, I guess. We got to think about what we're doing here. Well, that a plus delta x, that's really one of those delta x's. That a, that standalone a, is really a plus 0 delta x's. Now the question would be, how many delta x's would we have when all is said and done? Well, we have n subintervals, right? But the issue that we're going to run into here is if we were to say go from A to B, physically from A to B, we would start at point A, we'd end at point B. But when we graph this and create all those rectangles, the last interesting x coordinate is one short of B. All right, one short of whatever that location of B is. All right, so if I were to say a plus n delta x, that would get me all the way to B, right? Because I'd have n rectangles, and I would span that distance. But what I need to have is n minus 1 of those delta x's. All right. Now, when we plug them into f of x, because it's an arbitrary f of x, that actually, believe it or not, is kind of easy. Because, and specifically because it's arbitrary, all we could do is pop a f around each one of these and call it a day. I'm going to bring in a fresh new color. I'm going to go red. So f of, in each case, f of. Now it's going to get a little messier. We have to multiply each of those values by delta x because these are the y values. The y values give us the height of the rectangles, as we know. So for example, the f of a, that gives us the height of the rectangle. We also need the base, the length of the base, to get the area. So I have to multiply by delta x in each case. All right, so each one of these is going to get a delta x tacked on it, because again, we don't know what delta x is, except to say that it's b minus a over n, but since we don't know what b and a and n are, we might as well just leave it as delta x. All right, so I'm going to say copy, paste. I'm going to shrink it down a little bit. I'm going to give myself a little bit more space. Move some things. Just like about to go there. All right. So now I'm going to tack on a delta x. So let me get a green involved here so this we can start on. So delta x, delta x, delta x, delta x, and one more delta x. All right, then we have to add them all together, but again, because it's in general terms, like, okay, well, the best we could do is just slap some plus signs on here. All right, so that's what I'll do. I'm going to get the black marker back into play here. So plus, 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 and plus. All right, but we can generalize this because there isn't a whole heck of a lot that changes here. The only thing that actually changes is the coefficient of delta x. So if I take, just sort of pick your favorite one. I'll take the first one because it's the simplest. I kind of missed part of it, so let me, or actually I brought too much of it. Create an index for the delta x. Call that index I. And have the summation go from I equals 0, because that's our first substitution, because again, everything else remains the same. And the last substitution here, the last thing that I becomes in the sequence is n minus 1. And so we would have that summation rule to help us find the total area under the curve. And specifically by under the curve, I mean between the curve and the x-axis. Right, so the only thing left at this point, I mean, it's a whole heck of a lot left, but we do need to take a look and see how this plays out coming in from the right to the left. All right, and so that's going to involve another diagram.